Let us begin with the structure of methane, the simplest hydrocarbon. The formula of methane is CH4, only one carbon, fully saturated with 4 hydrogens connected to it. The thing to remember is that although we might write it in two-dimensional piece of paper as a flat structure, it is important to recall that the carbon here is sp3 hybridized, and therefore, as you can see on the picture on the right, it has a tetrahedral shape, and we should be able to look at it from different angles to get a feel for what the structure looks like. The next structure we're going to consider is ethane. Formula of ethane is C2H6. When we draw the structure, we can see a pattern in which one could look at these structures as being carbon-carbon connections, with each carbon having its entourage of hydrogens. However, don't forget that even though we can write it this way, we could write what we call a condensed formula, CH3CH3, to represent the way the hydrogens are organized with the carbons. Again, don't forget that in the three-dimensional structure, each carbon is, again, sp3 hybridized, and therefore there is a tetrahedral shape around each carbon. The next structure we're going to consider is the structure of propane. The chemical formula of propane is C3H8. Notice that because of the way the molecule is organized, we can visualize it perhaps as 3 carbon atoms connected to each other, each carbon having its own entourage of hydrogen atoms. So another way of representing this molecule is by writing what we call the condensed formula, CH3, CH2, CH3. Notice that again, when we look at the three-dimensional structure of the molecule on the right side, we can see that around each carbon there is a tetrahedral geometry, which generates a structure that if you look at it from the side is not completely straight like the one that we're showing in the Lewis structure on the left. So perhaps a better way of representing this and a shorter way is by using what is called the skeletal formula. To draw the skeletal formula, we draw the Lewis structure, perhaps indicating the proper angles between the carbons. And so what we do is we represent just the backbone of the carbon-carbon chain. And this is what we call the skeletal structure. Notice that it looks like a V, but of course, technically, you could actually do this structure the other way, kind of like bend it the other way, because all it's trying to represent is the fact that the carbon-carbon chain is not linear, it's actually bent. Let's look now at the structure of butane. This is the compound that has the formula C4H10. Again, we draw it as a connecting set of carbon atoms, each with its entourage of hydrogens. And once more, to represent the fact that it's not a linear arrangement, we go ahead and draw it on the left side here, the Lewis structure, with the angles between the carbons. Once more, if we'd like to represent this as a condensed structure, we would write it as CH3, CH2, CH2, CH3, but since the middle set of carbons pretty much are the same, we can draw it as CH3 parenthesis CH2 parenthesis 2, CH3. If we want to have a shorter way of representing this, we can use what is called a skeletal structure, which only shows the carbon-carbon backbone. And again, don't forget that these things are not static, these angles here, so you can actually flip the structure around if you want to. But the idea is that you're showing only the carbon-carbon backbone, and it is assumed that you understand that each one of those ends of segments or the junctions of segments represents a carbon with its entourage of hydrogens. At this point, we arrive at an interesting observation. When we drew the structure of butane, we automatically joined the carbons one next to the other. However, look at this structure here. This is called isobutane. Isobutane also has the formula C4H10. But as you can see, the carbons are connected in a different way. You can see there's a very central carbon connected to three other carbons, each with its entourage of hydrogens. You can see the molecular structure and shape on the right side. And of course, if we were to draw this, we would draw it in the form of, I don't know, maybe like a little Mercedes-Benz sign or something like that. The relationship between these two structures, that of butane, the previous one, and this one, isobutane, is something called isomers. An isomer is a compound that has the same formula but a different structure. In this case specifically, we call it a structural isomer because there is a difference in the ways that the atoms are connected to each other. This next structure is the compound pentane. Pentane would have the formula C5H12. Once more, to try to represent the zigzag shape of the carbon-carbon chain, on the Lewis structure on the left, we have also indicated the carbons not in a straight line, but at angles to each other. Again, if we want to represent this in a condensed way, we would then call it CH3 parenthesis CH2 parenthesis 3, because it's like we have three groups of the CH2 assembly and then CH3. We can also represent this more conveniently in the form of a skeletal structure, where we only show the carbon-carbon backbone, and each segment end here would represent a carbon with its corresponding entourage of hydrogens. Remember, each carbon here has to have 4 covalent bonds, either to other carbons or to hydrogen atoms. The structure that we're seeing here also has the formula C5H12. But in this case, the atoms are connected in a different way. This compound is called Isopentane. Notice that it has a branch off of the second carbon if you're looking at it from the left to the right. On the right side, you can see the three-dimensional shape of the molecule. And we could also write this in a skeletal form. Notice the branch shown on the second carbon starting from the left. Don't forget that we don't have to draw the structures exactly in this way. We can make all kinds of arrangements of things. For example, I could move this guy over here. I could move this guy further down this way. I could move this guy over here. So we can represent the structure in many different ways as long as the connections are intact. As we explained before, isopentane would be considered a structural isomer of pentane. It has the same chemical formula, but the carbons are connected in different ways. Let's look at another version of this, and this is the compound that is called Neopentane. Neopentane has the structure that we see here, and you can see it on the right where there is a central carbon that is connected exclusively to other carbon atoms. And of course, it looks kind of difficult to visualize here on the left, so sometimes it might be better to do the so-called skeletal structure. Again, notice that this compound, neopentane, is also a structural isomer. It has the same formula, C5H12, and it has different connections between the carbon-carbon atoms.